last time we ended talking about this example of a heterolytic or polar reaction, which is the addition of HCl to ethylene. And again, we're going to have a lot more to say about reactions like this in both Chapter 7 and Chapter 8. And Chapter 8 is going to be full of reactions just like this, because of course this does not have to be ethylene, it can be any alkene, nor does it have to be HCl. HBr and HI will also work. And there's scads of other reagents, which we'll learn about in Chapter 8. But they all have one thing in common, in that these reagents will all undergo addition reactions to alkenes. So that will be the same for all of them. And it's nice to have a unifying principle like that, I think. So now that we are familiar with this mechanism, we understand it has two steps. That's all the information we need to be able to draw at least a qualitative energy diagram. Maybe not quantitative. I know you were very quantitative about this stuff in Gen Chem. We're not going to be so much interested in that. As with so many things, we could go there if we wanted to. All that is still there. But I just want to make sure we understand qualitatively what's going on when we draw an energy diagram. And what we're going to do is draw the energy diagram for this reaction. Again, being very qualitative. We're not worrying about exact numbers here. But certainly on a typical energy diagram, on the vertical axis, you'll have some kind of energy. It might say E, it might say delta E, it might say delta G, it might even say delta H. And for a simple organic reaction like this, numerically, none of those are going to differ very much. So you'll see all of them used. And on the horizontal axis is a quantity known as the reaction coordinate. And basically what the reaction coordinate refers to is how advanced the reaction is. At the origin, we're 100% at starting materials, and as we move from the origin to the right, the reaction advances further and further until eventually it's all products. Some students have told me that they prefer to think of the horizontal axis as being time, and that's not exactly correct technically. Reaction coordinate isn't really exactly the same thing as time, but I'll be honest with you, it comes out the same if you think of it that way. You can think of time as increasing along the x-axis too. It may not be going necessarily linearly across the x-axis, but it's good enough. You'll get pretty much the same thing if you find it helpful to think about it that way. And what we have here then is a typical energy diagram for a reaction with two steps. And one thing you'll notice on the energy diagram is our starting material and our product, or our starting materials plural and our product. Products plural if there were more than one. Here there is just more than one. Can we also call the x-axis reaction progress? Sure, same thing as reaction coordinate. To me, they mean the same thing. And then we have this reactive intermediate in the middle, which we've spoken about. It's this carbocation that you see over here. And that's going to be our reactive intermediate. It's very typical for reactive intermediates to be much higher in energy than either the starting material or the product. I chose its location somewhat arbitrarily in terms of height off of the x-axis. But I would expect them ordinarily to be quite a bit higher in energy than either the starting material or the product. And that's typically what a reaction energy diagram will look like for any reaction with two steps. What if the reaction had three steps? Well, it would go up through a transition state, you'd hit an intermediate, then over another activation barrier and you'd hit another intermediate. Might be slightly above or slightly below in energy, could be either would be acceptable. And then one last activation hump and it goes to the products. So basically you need to have, I would say, I'm trying to think how to say this. It's two steps, so there's one intermediate. And rather than writing this down, I want to treat you guys like adults. But this is going to wind up on YouTube. Say hi, YouTube, everyone. And so you can watch me say this as many times as you like. But basically, as I think about it, the way it works out is, I think, it's funny, I think that there's going to be one fewer intermediate than the number of steps. So there's 2 steps to the reaction, we have 1 intermediate. And I don't see how it could be otherwise than that. I don't know that there's necessarily a rule that states that, but I think that's always going to have to be the case. So what if a reaction, for instance, had only 1 step? And we will learn a lot of reactions that have only 1 step. Well, 1 minus 1 is 0. There will be no intermediates. You'll just start at your starting material, you'll go over an activation barrier at a transition state, and then down to the product. So we'll see examples of all of these when we do energy diagrams later on. We'll come back to them from time to time, both this term and next term, because they're useful to help us understand reactions and to help us get an idea of what those mechanisms look like. So they're just helpful for helping us visualize these things, I would say. And so, so my plan just now is to go over all of the anatomy and parts, if you will, of a typical energy diagram, especially making clear the difference between transition states and reactive intermediates. They are different critters. And then we'll apply that to this mechanism. Later on, we'll also cover the Hammond Postulate, which really is in chapter 7, which is part of this unit's material, so it's fine if I go a little bit out of order. It's just a thing about me, I guess. I just can't resist mentioning it now. It seems to me to be too relevant. So even though it's in section 710, I think it makes some sense to bring it forward and mention it now. So that's kind of my plan here. And we'll also talk about some of these energy differences. There are going to be quantities that you talked about in Gen Chem. Actually, now's as good a time as any there. This energy difference between the starting material and the product, hopefully you remember from Gen Chem, that's going to be nothing other than the energy of reaction, or Gibbs energy of reaction, if you will. And in this particular case, we find that the Gibbs energy of reaction is negative because the product is lower in energy than the starting material. And that will often be the case. I'm just making that very reasonable guess because I know that reactions of this type are very, very spontaneous at practically all temperatures. So, so I think it's reasonable to conclude that these products are more stable than the starting materials. And incidentally, I think we also can come to the conclusion, something we already discussed, is that a reaction of this type, of an addition reaction to alkenes, not just this one, this would be true of any addition reaction to alkenes. We've already said that it's very reasonable to guess that delta S for this reaction is negative, right? It's entropically unfavored or disfavored because we're going from 2 particles down to 1. The molecularity goes down. So the disorder decreases, and that's unfavorable in terms of entropy. So I think it's very reasonable then also to predict that delta H had better also be negative. This is going to be a reaction that's driven by enthalpy, by virtue of being an exothermic process. But processes like this occur all the time in nature and living systems, are used in industry, and I would certainly bet pretty much the whole thing that this reaction is a negative delta G, that it's exergonic. If you were looking at an endergonic process, then of course the product would be higher in energy than the starting material. So that's how you'll know what to put. You'll get to practice these things also on OWL. So this energy difference, though, between the starting material and the product is going to be your energy of reaction. And of course, if we'd written delta H here, then technically we'd have to write delta H of reaction. You know, technically you're supposed to make that match. I would expect those two to be pretty similar numerically. Right, so, but that's always going to be the case. Sometimes delta G will be negative, other times it might be positive, and you'll have to change the shape of the graph accordingly. And I wouldn't expect you to know any numbers. You know, you'd have to put that, you'd have to make that decision based on what you're given. Good, and as always, I think you know the basic rules by now. Certainly as far as my exams are concerned, you already know when it comes to knowing what you have to put down, you have to do everything it says. You don't have to do anything it doesn't say. Within reason, of course. You know, I will expect you guys to be reasonable. If someone were to bring their exam back to me later and say, look, they took off points for having 5 bonds to carbon, but the problem didn't say you can't have 5 bonds to carbon. Well, you know, that's clearly implied by the class material. I don't think anyone would have too much sympathy for a case like that. Good. So that's one energy difference. What about this other one? The energy difference between the starting materials and the first transition state. And we still have to talk about what transition states are. That, of course, is going to be your activation energy. And I've seen that written delta G double dagger. I'm also perfectly fine with EA. I think that's fine. Either one of the two is fine. Maybe we'll call this one the first activation energy, EA1. The second activation energy would, of course, be this small amount of energy to get over that second activation barrier. That would be EA2. And again, you'll know what you need to put based on the phrasing of the question. But certainly, I would expect you guys could label any or all of these, and you'll get practice doing that in OWL. And again, if there were then a second step, we'd find there is a third activation energy, a third barrier to get over. So that's all going to depend on the energy diagram in question. So before we get to the differences between transition states and intermediates, I just also like us to note, you'll notice I've also labeled what the species are that are present at each of these states. So here we've got our starting materials, and I've got both of them, including the inorganic starting material, HCl. And you'll notice over here, even though we're mainly interested in the carbocation, I'm including the chloride ion, and we have to do that. The reason is, although I've already confessed to you guys that we organic chemists tend to get a little bit sloppy about balancing reaction equations for mass. When it comes to energy diagrams, we can't afford to be sloppy. We need to make sure that, that at all stages along the way, it's balanced for mass, because otherwise we're not comparing apples to apples. And then the energy differences, even in a qualitative sense, won't be correct. So in order for the reaction energy diagram to have the right shape, we need to be sure that we're always balancing for mass. Lots of times we're sloppy, we organic chemists. Not here. We can't afford to be sloppy. We need to make sure everything's balanced for mass all along the way. And by the way, you'll also find at each stage it's also balanced for charge, which is nice to know. Of course, in the beginning, we've got 2 neutral molecules, total charge is 0. At this intermediate, we've got a carbocation intermediate, which is a +1 charge, and also a chloride ion, which is a -1 charge. That again adds up to 0. And of course, the product is a single neutral molecule, total charge 0. So these are nice checks that you can use to make sure that you're considering everything correctly. And so with those 2 energy differences, or 3 energy differences, those I think are the ones of major importance. So then let's get to this whole idea of what is a transition state and how is that different from an intermediate like this carbocation. The first thing to be aware of is that intermediates are real species, meaning that they have a proper Lewis structure that we can draw, and they also are things that we can detect experimentally. And in the case of this reaction, it's known experimentally and been verified experimentally that we do go through one intermediate. We have that carbocation intermediate. There are ways of detecting those things using spectroscopy or special trapping techniques. These sorts of things have been in use for practically a century. Maybe not quite, but pretty close, if not quite a century. And so intermediates are always real species, no exception. Transition states, though, are not real species. They're not things that we can detect experimentally. And as to what a transition state actually is, I'll get to in a moment, but I realized I forgot something else. Please don't be overly detailed oriented. I don't expect you to memorize this exact shape when you draw energy diagrams. Some of my decisions were kind of arbitrary. I put TS1 higher in energy than TS2. I don't know that for sure. I could have made them the same energy. I could have made TS2 a little higher than TS1. Absent being given actual numbers, you know, we don't know that type of thing. And I wouldn't expect you to either. So little variations like that I consider perfectly acceptable. Make sense? Oh, yes. Can a reaction ever get past? You mean, can individual molecules not make it over the second barrier? Absolutely. Happens all the time. Some might not make it over the first barrier. It's actually a very good question. He said, for those of you in chat, he said, can it happen that a molecule will not make it over this second energy barrier? Absolutely. Some of them won't make it over the first one. Every once in a great while, you might find one that goes over the first barrier and then reverts back to starting material. Sure. So the reason I think this is a very good question and a very important point is you need to understand, this is a common misconception among students. When we draw a mechanism like this, we're not saying that every molecule, every single one does exactly this and, you know, nothing else. There are cases of intermediates reverting back to starting materials. There might once in a blue moon even be one that reverts all the way from product back to starting material. However, with this energy difference being negative, I think over time, we can expect the equilibrium to favor the product very strongly. And I think as long as we wait enough, we'll get a very good yield of this product. So, but it doesn't mean that every single molecule does exactly this, and then every single one of those does exactly this, and then every single one gives the product, and that's it. That's not what's implied by drawing a reaction mechanism. Real life is somewhat sloppier than that. It simply means that over time, the equilibrium we would expect to favor formation of the product. And certainly if we chose our reaction conditions correctly and waited long enough, you know, we can hopefully expect to get a very high yield of the product. Good, so where was I? I was talking about transition. Oh yes, I had made the point that, you know, I put these relative heights as being somewhat arbitrary. Same with these, you know. I did want to be sure to make the starting material higher in energy than the product, but, you know, I'm not going to get out a ruler and measure an exact number of millimeters or something like that. You know, this is a qualitative energy diagram. We're not using specific numbers, nor do I expect you to memorize specific numbers. Good, so we've said what a transition state is not. Unlike reactive intermediates, transition states are not real species. Now, what is the difference between the number of steps in a reaction and the number of transition states? Al differentiates them, and I'm not sure why. While they refer to different quantities, I think in general, you're gonna have to have one more transition state than steps in the reaction. And the way you know is because for each step, you're gonna make an intermediate. For between any two species, there's gonna be an intermediate. If, you know, depending on the number of steps of reaction. Let me try again on that. That wasn't as clear as I would like. In this case, we know from the mechanism, because we know the mechanism. You can't really do this unless you know the mechanism. But we know that the mechanism takes two steps. And so the first one has to go to an intermediate, not straight to the product. If it went straight to the product, then there'd be just one step. So the first step is from the starting material to this intermediate, and the second step is intermediate to product. So what was the rule that I sort of came up with? I think this will always work. I can't come up with an exception. Is that there's going to be one fewer intermediate than the number of steps. Which actually, now that I think about it, the number of transition states is going to be the same as the number of steps, isn't it? Yeah, number of steps is the same as the number of, let's say concave humps like this, right? Local maxima sounds better than humps. So your transition states are going to be local maxima. Meanwhile, all of your real species, like the starting material, like the product, like the intermediate, those are all going to be local minima. So that's going to be another difference between transition states and the real species, the intermediates and the starting material and products. Now you're asking about the number of steps in a reaction and number of transition states. As I think about it, the two have to be equal, but I don't know that there's a rule to memorize that states that. I think that's just kind of a nice coincidence. But I think that is going to hold in general. that the number of steps in the reaction will equal the number of transition states. I can't come up with a counterexample. So, and again, I'm not going to write it down because it's going to be on YouTube. Hi, YouTube. The number of intermediates will be one fewer than the number of steps in the reaction. And the number of transition states will be the same as the number of steps in the reaction. I don't think it's possible for there to be an exception. So that will be on YouTube. You can watch me say that as many times as you like, although personally, I would hope you would find it boring after about once or twice. Good. So again, we still haven't really investigated yet what transition states are. We've talked about what they are not, but we haven't covered what they are. We've said that they're not real species, and that's fine. So what then is a transition state? And this is sort of my definition. I don't know how rigorous this definition is. I think it would generally hold up. But to me, a transition state is kind of a cartoony representation. And it's a cartoony representation of the following thing. If you could shrink yourself down to molecular size and watch a reaction take place, and then, if not only that, you also had the power to stop time at exactly the halfway point of a step, when it's exactly midway to completion, when the step is exactly halfway complete, what would you see? That, to me, is what a transition state is. It's a cartoony representation of what the midpoint of a step might look like. And again, you'll find that in my class notes. But that's the best description I think I can give you. Now, normally, we don't draw transition states. And again, you know the rules. You have to do everything the question says. You don't have to do anything it doesn't say. So normally, we don't draw transition states. You might have to occasionally. But it's helpful to know about them even if you're not asked to draw them, because they give us insight into understanding the reaction. And that brings me to the Hammond Postulate, which I just can't resist mentioning at this juncture. It's too relevant. So, you know, if God forbid I were going to write my own textbook, I'd probably put it in this same chapter. But I don't really wish for that level of insanity. I've got enough already as it is. But be that as it may, the Hammond Postulate is one of these things, I already said this to a couple of you before class, that we unfortunately find in textbooks of all flavors, where they take something and make it terribly, terribly complicated when it's not. And it just really irks me. It really burns my bacon. Because there's so much stuff in this world that legit is difficult and complicated. Why on earth would we take something dirt simple and make it complicated? So this is the way I like to present Hammond's postulate. Hammond's postulate tells us something about what transition states look like. So first of all, that's how I would like you to categorize Hammond's postulate. It helps us to know what a transition state looks like. And Hammond's postulate just says the following. It says, if you want to know what a particular transition state looks like that you're looking at in an energy diagram, you compare it to the two real species on either side. And there will always be two real species on either side of a transition state. Always. No exceptions. Has to be two real species. That's the definition of what a transition state is almost. It's this thing that occurs as an energy maximum between two real species. And so Hammond's postulate says you need to compare the transition state to the two surrounding real species. And if I stopped here and asked you to make a wild guess which of those two species the transition state is going to look like, the one that's further away in energy or the one that's closer in energy, I'm confident you would all make the same wild guess that it looks more like the species to which it's closer in energy. And that's exactly right. Bingo. That's all Hammond postulate says. So all of the other verbiage, all of the other spinach, all of the other stuff that they throw in your way, don't even just let it slide right off you. Hammond's postulate just says that if you want to know something about what a transition state looks like in an energy diagram, it will look like the surrounding species, the one of the two surrounding real species to which it is closer in energy. That's it. It will look more like that than like the other species. That's what the Hammond postulate says. And so, like I said, we don't normally draw transition states. Certainly, if it doesn't say to draw it, we're not going to draw it. But if I were to try to draw the transition states, I certainly could do that. And that's something I think we could learn something from. It looks like the first transition state is closer in energy to the carbocation intermediate than it is to the starting material. That tells me that the transition state looks more like the carbocation than it looks like the starting material. And that gives us information about the reaction. So if I were going to, yes, some good discussion on transition states. Yep, I agree. I think that's exactly right. Couldn't have said it any better myself. Good, so the transition state is going to look more like the carbocation than like the starting material. What does that mean? Well, it means that the double bond is almost completely gone between the two carbon atoms. There might be a tiny bit of double bond character left, but breaking of that bond is very advanced. And it also tells me that the new carbon-hydrogen bond is almost fully formed. Maybe not quite 100%. Okay, yes. I'm sorry, do you need to know what? Yeah, you can apply the Hammond postulate to any reaction. The question is if you have to know the relationship of Hammond's postulate to other reactions? Sure, but you can only really draw the energy diagram if you know the mechanism. So if you don't know the mechanism, you can't draw the energy diagram, you know. But as long as you can draw a decent energy diagram, which generally you'll know the mechanism for, I'll put it to, I think what you're asking, I could not draw the energy diagram of a reaction if I did not know the mechanism. Oh, I think what you're asking maybe is, could you be expected to apply Hammond's postulate to an energy diagram that looks different from this one? Absolutely. Is that kind of what you meant? Yeah, and you'll get practice doing that with OWL. Certainly. And then the way it's done, you'll see where everything is. So you'll be able to, you'll have the possibility, you'll at least be able in principle to draw the right conclusions, I think. Yeah, OWL actually has some problems that give you energy diagrams. And remember, I've posted old exams. So I don't promise yours will be just like that, but it at least gives you an idea. Good, other questions then? Where are we at? 12:33. Good, so I'm trying to remember where I was. Oh, I was drawing the first transition state, right. So I would say formation of this new carbon-hydrogen bond is going to be very advanced. And there's going to be a great deal of plus charge, almost a full plus charge in that carbon. Maybe not quite a full carbocation, but pretty close. And it looks to me like the bond between the hydrogen and chlorine will be almost completely broken. And there'll be a very high degree of minus charge. I'll put delta minus by the chlorine. So something like that. I mean, all of these angles are negotiable. That's not the issue here. I don't say it is to look exactly like that. I'm just trying to show how it links up, and I'm trying my best to show the difference between bonds that are almost fully formed and bonds that are almost fully broken. I would guess, based on its position on the energy diagram, that this transition state, normally we use square brackets to denote transition states. Sometimes they put a double dagger also. But that would be my best guess, is it would look something like that. Certainly a lot more like a carbocation than like the alkene. What would it look like if it were more like the alkene? Well, then the double bond would be almost still fully formed, right? It would only have just started to break. And I'm having trouble thinking of an example of something like that. But if the Hammond postulate said that, then that's what we do. We would show that if it were the opposite, we would show that very little carbon-hydrogen bond formation has yet taken place. And the hydrogen-chlorine bond is still, if it were in the opposite situation, that would still be mostly in place and not have broken to any large extent at all. But given where the transition state is and how it's much closer in energy to the carbocation, if I had to make my best guess, I think that transition state would look something like that. What about the second transition state? Well, you'll notice that one also is much closer in energy to the carbocation than it is to the product. So we would just reflect that. That tells me that formation of the new carbon-chlorine bond is not very much advanced at all. I would guess that this would still look mostly like a carbocation, that we would have certainly now only a single bond here. Now this carbon-hydrogen bond is fully formed. There would be, I would guess, a lot of plus charge left on that carbon. And maybe my chloride ion has just barely started to make friends with that carbon. Maybe there's a little bit of orbital overlap there. Just the barest beginnings of forming a bond with a large amount of minus charge still on the chlorine. So maybe something like that. And again, exact angles between and distances, that's negotiable. But I think you'll agree this does a fairly good job at communicating that rather this transition state looks much more like the carbocation than it looks like the product. If it looked more like the product, then we would show the carbon-chlorine bond as being mostly formed. That formation of that bond would be very advanced. But the opposite is true here. I would expect the formation of that bond to have hardly progressed at all. And maybe something like this is how you would draw it. So like I said, normally we will not be drawing transition states. But if you do, that's how you would approach it. And again, normally we use square brackets and often even this double dagger to show that we're talking about a transition state. This still gives us useful information about the reaction, even if we don't have to draw that for points on an exam. It tells us something about the reaction. It lets us know that the energy diagram is a certain shape, and that's reflected in what happens over the course of the reaction. So that's why I really think the Hammond postulate, in addition to being way, way, way simpler than they make it out to be, is actually very powerful. It's quite profound in its simplicity. But it is very simple. It's no more complicated than that. And I think that's about all I can think of to say. Yes? The top right. It's a double dagger, because sometimes they write like delta G double dagger for activation energies, referring to transition states. He's asking what the symbol is by the square brackets, right? Yeah, it's a double dagger. And you'll commonly see it written there. It just means that the species inside the square brackets is not a real species, it's a transition state. So, and again, neither of these things could we actually detect. They are not real species. They're just our best good faith effort at showing what we might be able to see at the halfway point of that step. That's basically what transition states are for, but they're not real species. They can't be experimentally detected. They don't occur as real things in nature. Intermediates do, transition states don't. Good, other questions then, or in chat as well. All right, and again, has everyone registered their attendance? I'm just taking attendance today. I really don't like to do that too often because I want to the best of my ability to make it have been worth your money to buy the Reef app, but sometimes we just don't have the time, and I don't really have more than 2 Reef polling type questions ready for each week. Good. And that's again for those semesters where I teach both Monday, Wednesday, Friday, and Tuesday, Thursday. So we can keep kind of in the same place. Good. I think with that, we're ready to start considering alkenes in a little more detail. So chapters 7 and 8 really are both about alkenes. They're saving most of the heavy duty sort of reactions until chapter 8. But chapter 7 is going to lay the foundation. And so, like I think I've said, I think we'll start on Monday with this business about a degree of unsaturation, which can also be called index of hydrogen deficiency. I just am aware that that's not a good topic to end a class with, because goodness knows everyone's attention is wavering, including mine. You know, we're all tired. It's the end of the week. I think that's a good thing to start on Monday on. We'll consider relative stability of different alkenes depending on how they're substituted. That all I think plays very well together. What I would like to get through today is at least some pointers on alkene nomenclature. I don't think we'll do a whole bunch of examples because, as always, I really think nomenclature is something best practiced on your own. I think that's the best way to learn it. You'll get to practice that in the chapter 7 owls. But I can at least get you guys started. And in order to get you guys started, I will say, as with everything else really, knowing how to name alkanes and alkyl halides and things like this, you already know 90%, I think, if not more, of what it takes to name alkenes. The main difference is, of course, you'll have to say in your name where the double bond is. And normally in an acyclic compound, I would want to put the double bond closer to one end than to the other. But again, if you're ever in doubt, if you have two possible names, then you can pick the better one, which will have the smaller sum when you add up all the numbers. And I think there will always be a better name. I don't think it's even possible to have a tie. At least I've never seen an example of that. And of course, you will use your numbers to show where the double bond starts. The carbon that the double bond starts at is what you'll do. And likewise with cyclic alkenes, it could vary, I could imagine. But again, you'll want to consider how to number your carbons such that the sum of all of the numbers is as small as possible. That's certainly what I would aim for. In addition, of course, when you've got alkenes, you have to consider the possibility of cis and trans stereoisomers, which we're going to talk about in a moment. And then if the cis-trans system gets broken, which you'll find is not hard to do, then we've got this E and Z system, which we use instead. That will always apply. The other thing I suppose I should say about cycloalkenes is I think you can see, certainly if you make a model, but probably even from drawing it, that small and medium ring cycloalkenes must always be cis. Because you can't, there's not enough space in the ring to accommodate a trans double bond. It can't fit, it's too strained. I've heard it's possible to make a cyclic alkene that has a trans double bond, but this ring has got to be pretty big. I think at least something like 9 or 10 carbons in order for it to be at all stable. Certainly cyclohexene, cyclopentene, those are going to be always cis. And so for that reason, we don't even say cis cyclohexene. Sounds silly. Of course it's cis. You couldn't fit a trans double bond in a 6-membered ring. So we don't even bother mentioning that it's cis. It's understood. Good. Oh, and I'll also mention just one other thing. Guess what? If you know how to name alkenes, you know everything you need to know to name alkynes. So whereas you'll use that -ene suffix for double bonds. And by the way, if you have a situation with multiple double bonds, then you'll use terms like diene or triene, just as you would probably have guessed. But when you go on to alkynes, it's exactly the same, except you use -ine, Y-N-E. And at that point, by the way, you don't even need to worry about cis and trans. That's gone, right? Because the carbons are sp hybridized. And so there is no possibility of cis or trans. And then this other business, I was going to talk about that someone's bringing up in chat. There's also two different conventions, I guess you would say, well, let's do like a real easy one, maybe. 1, 2, 3, 4, 5, 6. You can call that 1 hexene. That's pretty obvious. Or what the person in chat is talking about is it's also acceptable to put the number in between, hex 1-ene. It looks a little funny, and Al will point this out to you. I consider both names acceptable. I think they're both equally good. I will say, though, that this is the convention that we use mostly in the US. They mostly do it like this over in Europe. Whenever I see someone naming alkenes like this, oh, I then am not surprised to find they're from Germany or France or Switzerland or what have you. Not to put them down, but that's often the case. They tend to name alkenes that way over in continental Europe. But in the US, we mostly name alkenes this way. Good. So what about cis and trans? Well, we do run into a stereochemical issue with alkenes, which is that even a simple molecule like 2-butene has 2 stereoisomers that are possible. And those are they. And I've already heard people talking about cis and trans alkenes. It's possible that for some of you, your Gen Chem professor talked about this situation. But you need to be aware that these are different compounds. You can't interconvert them. The reason we know that is because you can't rotate around a double bond the way you can rotate around a single bond. So these 2 molecules are permanently different, and they have different properties. And so we can't call them 2-butene. We need to be more specific. I'll also say something else. It's not unheard of that you might see such molecules as these 2 isomers called diastereomers, the same term we used in chapter 5. And it's not wrong. These 2 fall under the definition of diastereomers. We said diastereomers are 2 stereoisomers that are not mirror images of one another. And indeed, you'll have to admit, those 2 are stereoisomers. They're not constitutional isomers because all the connections are the same. But they also are not mirror images. So it's perfectly acceptable to call cis trans or EZ stereoisomers diastereomers. Yes? Sorry. That's true. They are sp2 hybridized, and there are no chiral carbons. But the molecules as a whole fall under the definition of diastereomers anyway. Wouldn't you have to have chiral carbons in order for them to be able to be diastereomers? The answer is no. Nope, diastereomers just means that you've got 2 stereoisomers that are not mirror images. To be stereoisomers, does it have to have chiral carbons and be mirror images? Again, no. Think of cis 1,2 dimethylcyclohexane and trans 1,2 dimethylcyclohexane. Those are stereoisomers. And you would also not be wrong in calling them diastereomers, though they're usually just called stereoisomers. So what you need to know is that that diastereomers are defined as 2 or more stereoisomers, and we've defined stereoisomers. They're species that have the same formula, the same connectivity, so all the bonds are the same, but the atoms are arranged differently in 3-dimensional space. And so as long as you have any 2 stereoisomers of any kind, whether with chiral carbons or not, that are not mirror images, we can call them diastereomers. Now, it is true that these things will not have enantiomers. For that, you have to have chiral carbons, I would say. But for diastereomers, you don't. Does that clear it up at all? Yeah, it does sound a little strange at first, and I don't usually think of calling these guys diastereomers, but you can. It's not unheard of. So, we need a way of distinguishing these, and sometimes if you need a visual aid, you can draw a dotted line down either or both of those double bonds. And in cases of di-substituted alkenes like this one, we call the alkene a cis alkene if the 2 groups are on the same side of the double bond, and trans if on opposite sides. So this guy is cis 2-butene. And this one would be trans 2-butene. But again, and I'm starting to run out of time here, you will very quickly discover that it's very easy to break that system. What if you had a compound like this? Well, is that cis or trans? Well, neither, right? You could say that this methyl group is cis to the ethyl group. That's correct. You could also say the chlorine is trans to the ethyl group. That's true. But that doesn't tell us how to name the compound. And that's where the E and Z system comes in. So, and the great thing is you already know everything you need to know in order to determine E versus Z. What you're going to do is compare the two groups on either of the two alkene carbons. It doesn't matter which you start with. And then you do the same thing at the other one, and you compare the two groups using the Conning-Gold-Prelog rules. So you know that already. And in fact, it's easier, because instead of having to compare 4 things and turn your steering wheel and all that, you just need to compare 2 things here and 2 things here. And it becomes very straightforward. So here, for instance, we've got the carbon in an ethyl group versus the hydrogen. Clearly, the carbon wins. Here, you've got a chlorine versus a carbon. The chlorine obviously wins. So it's very simple. And then you observe whether the 2 winning groups are on opposite sides of the double bond or on the same side. And we assign the configuration E if they're on opposite sides of the double bond. And we call the configuration Z if they're on the same side of the double bond. And I'll show you in a moment where those terms originate from. So I would call this guy, since they're on opposite sides, let's see. 1, 2, 3, 4, 5. We'll start with carbon 1 over here. This is named as a pentene. Again, this methyl group is included in the carbon chain. So that's taken care of by calling it a pentene. And I would say the double bond starts at carbon 2 and also the chlorine is there. So to me, this would be E, 2-chloro, 2-pentene. I think that's the best name. Now, where do these E and Z, where do they come from? If you're one of the few, the proud, that have taken German in high school, or maybe you spoke it at home, you just won a prize for that, because they come from German words. E is short for entgegen, which means yonder over on the other side, and Z is short for zusammen, which means together. If you're not among the few and the proud, the most common mnemonic device I've heard is Zame Zide. It's stupid, but it works. So you're welcome to use that. Will all trans compounds be E? That's a good question, because you can always use E and Z. You could call cis-2-butene Z2-butene. It's perfectly correct. And you can call trans-2-butene E2-butene. So I think the answer to the question, Chad, is yes. If a double bond is clearly trans, it will always be E. If it's clearly cis, it will always be Z. But when you have one of these situations where it's not either cis or trans, then you need to use E or Z. I think you need I think it's only defined for double bonds. So it's not used for like cycloalkanes. And triple bonds, of course, can't be either cis or trans because they're linear. Other than that, I've gone over a fair bit. So sorry about that. I will see you all on Monday. Have a great weekend.